Today we're going to look at the simulation of relaxation and the treatment of relaxation phenomena in SpinDynamica. So just to orient ourselves, if you remember, I said that the state of the spin ensemble, which is the way in magnetic resonance theory we deal with the quantum state of the macroscopic system containing many spin systems, is done by specifying what's called the density operator. So this rho is the density operator. And the density operator evolves through a differential equation called the Liouville-von Neumann equation, or LVD. It's a very simple differential equation. The partial derivative of this operator with respect to time is simply given by a superoperator acting on the density operator, where this superoperator is called the Liouvillean. And as I discussed last time, the Liouvillean has two parts to it. There's a coherent part, which represents those parts of which generators, which driving forces for the evolution of the spin system are the same for all members of the ensemble. So that's what we mean by coherent. And an incoherent part for it, which represents fluctuations and statistically fluctuating interactions, which are not the same at all points in time for different members of the spin ensemble. And the coherent part is given by the Hamiltonian, the coherent Hamiltonian acting on the spin system, where here the hat implies a commutation superoperator. So these are the chemical shift terms, the J couplings, the dipole couplings, the quadrupole couplings, whatever else one has going on in the spin system, or the interaction with radio frequency pulses as well. That all goes into this coherent Hamiltonian, and then the superoperator is formed, the commutation superoperator of it, multiplied by minus I, and that's the coherent part of the Liouvillean. And then we have the incoherent part of the Liouvillean, which represents the effect of fluctuating interactions. And that contains the relaxation superoperator, which is usually called gamma, with a hat on to indicate it's a superoperator. And in general, we may have a kinetic exchange superoperator as well, to deal with slow motions or chemical exchange processes. And I'm not going to deal with this kinetic exchange part today, in part because at the time of recording this lecture, SpinDynamica doesn't include an implementation of it. So I'm only going to talk about the relaxation part at this point. So that means that the implementation in SpinDynamica as it stands now is restricted to problems which can be described by the relaxation superoperator and the coherent Hamiltonian. And this implies that one can model the fluctuating Hamiltonian, the incoherent Hamiltonian, using this relaxation superoperator. That's true if the fluctuations are sufficiently rapid. That regime is often called the Redfield limit or Redfield regime. If you want to be a bit more quantitative about that, what is that regime? It would be a statement something like this, that if you have a fluctuating Hamiltonian, for example, it could be dipole-dipole couplings between spins in a rotating molecule. If we take the magnitude of that operator, and there's a mathematical way of doing that, called the norm of the operator, and multiply it by its correlation time, which says how rapidly the correlation function of that particular operator decays, then that product should be small. And we can handle many important problems in magnetic resonance using this approximation. So examples we're going to look at today include relaxation by dipole-dipole couplings, cross-correlated relaxation phenomena, the narrowing of lines by relaxation in some cases, and the phenomenon of long-lived states. So there's a wide range of magnetic resonance phenomena which are covered by this, but there are also problems involving slower processes. Often many of them go under the term chemical exchange, which cannot be handled within this formalism, so we should be aware of that. Can expect, though, that in the near future then SpinDynamica will also be able to handle kinetic exchange. It's just not quite ready at this point. Okay, so now we're going to look at the relaxation superoperator and how it may be specified in SpinDynamica. So let's just look at the relaxation superoperator. And in SpinDynamica, there's two different ways of specifying a relaxation superoperator. One is called phenomenological. Now what that means is that one simply specifies the relaxation rate constants without concerning oneself with the microscopic mechanism of what that relaxation, where that relaxation comes from, or what causes the relaxation. So that means you can specify T1, T2 values and other relaxation rate constants which characterize the relaxation. And that's a relatively simple way of specifying the relaxation without going into the details. And then one has all the tools available for specifying mechanistic relaxation superoperators, in which you really specify the detailed mechanism. And they can be essentially arbitrarily complicated for any relaxation mechanism or model of motion, providing it's in the Redfield limit. So that's general for any mechanism or combination of mechanisms in the Redfield regime. And we'll look first of all at the phenomenological approach, which is probably the easiest entry into specifying relaxation and analyzing what that does in magnetic resonance experiments. So if I switch now to the Mathematica notebook, and I'll start SpinDynamica by executing the needs command. And then we're going to look at this object called with this very long name, which I apologize for, but sometimes it's better to be clear than to be brief. Phenomenological relaxation superoperator. Any symbol in SpinDynamica or in Mathematica one can access the documentation for it, or at least some usage message, by executing it with a question mark in front. So in this case, we get a description from the how to use phenomenological relaxation superoperator in SpinDynamica. And in common with most commands, there are many different ways, different syntaxes which can be used with this. One can specify, for example, with a simple syntax where one says phenomenological relaxation superoperator with a single argument, that just constructs a relaxation superoperator with the same relaxation constant for all spins with equal T1 and T2 values. If you give it two numbers, then it uses two different T1 and T2 values, but they're still the same for all the spins. And there are many general forms of the syntax where you can specify individual T1 and T2 values for different spins. So we won't go into all of those, but if I, for example, start with a single spin-a-half system, and we'll set up an operator basis using the Cartesian product operators, which in this case, for single spin-a-half, involve just the unity operator and then the Ix, Iy, and Iz operators with normalization constants, which one can examine using the operator norm routine. If we map that routine using the Mathematica /at, which is a way of saying mapping a function onto a list, applying the function to each member of the list. This shows that all of those operators are normalized, have a norm of 1. So then we can form the relaxation superoperator, in this case with different values for T1 and T2, and take its matrix representation in this operator basis, and then examine what it looks like. And we see we have a 4 by 4 matrix, four dimensions of 4 because we have 4 basis operators. The first row and the first column are all zeros, and that's because the unity operator does not relax with anything else. So very often we can ignore the unity operator for that reason. However, shortly we're going to come into the topic of thermalization, and then in fact we'll find that situation no longer applies. But for now, the unity operator is disconnected from all the other operators in the basis. And we have just 3 diagonal elements given by 1 over T2 for the second and third operators, which are Ix and Iy. So transverse, that's where we have relaxation rate constants of 1 over T2 for them, and 1 over T1 for the Z operator. And these elements are all negative, and that's because relaxation causes decay. So the negative elements of relaxation matrices, or in general the negative eigenvalues, refer to the fact that particular mode of spin order always decays under relaxation. Its time derivative is negative. So that's where the negative sign comes from. So this is a very simple matrix which, if we decoded it into a differential equation, we would be writing something like this, that the time derivative of the expectation value of the unity operator, the expectation value of Ix, Iy, and Iz, okay, multiplied by these normalization factors, will be given by this 4 by 4 matrix, and again the same expectation values, Ix, root 2, Iy, root 2, Iz, root 2, zeros everywhere, but the relaxation rate constants on the diagonal, where R2 is 1 over T2 and R1 is 1 over T1, and zeros everywhere else. And this actually just corresponds to the Bloch equations without the application of any magnetic fields. So the Bloch equations are just a special case of the Liouville von Neumann equation for when we have a single spin-a-half system and when we just have a phenomenological relaxation superoperator. And we can use this relaxation superoperator in calculations, as we'll see in a minute. Now, if we have an ensemble of systems with more than a single spin-a-half, then we can look at that too. So if we have 2 spin systems, if we just remind ourselves about that, in the default basis of Hilbert space, we have the 4 states, alpha, alpha, beta, alpha, and so on. And again, we can use a Cartesian operator basis. And this time we have a larger set of basis operators, again the unity operator, now a set of single spin operators, x, y, z, but now for the 2 spins, and then product operators consisting of products of the Cartesian operators for the 2 spins. If we want to know how many operators we have in a basis, we could use the operator basis dimension, which tells us that we have 16 operators in this basis. And again, we can form a phenomenological relaxation superoperator for the 2-spin system. In this case, we're specifying, with this syntax, we're specifying T1, and assuming that the T1 is the same for all the spins, and we're specifying T2 and assuming T2 is the same for both spins as well. And with this time we get a 16 by 16 matrix with lots of elements in it. You can see all the T2s, the T1s. Now, when one comes to the later rows and columns in this, then one's coming into the product operators. So this will probably refer to perhaps an operator I1x, or rather I1x, I2z, for example. And the assumption here is that such operators have decay rates given just by the sums of the two rates for the individual operators. That's an assumption, actually, which is called an assumption of uncorrelated random fields. The two spins are relaxed by fluctuating fields, but those two fields are uncorrelated. The fluctuations in one does not give any information as to which would enable you to predict what the other field would be doing at that particular point in time. So basically, in the uncorrelated random field approximation, then the relaxation of, say, a term 2I1x, I2z is approximated, the relaxation rate constant of that is approximated as the relaxation rate constant of just the I1x operator, R2, since it's a transverse operator, would decay with a rate constant R2, because T2 refers to transverse operators. And then the Z operator, being a longitudinal operator, would decay with a rate constant R1, where here R2 is 1 over T2 and R1 is 1 over T1. So without fuss, phenomenological relaxation superoperator makes that assumption as a default. One can specify the correlation as well, but I'm not going to go into that. Okay, so that's a pretty easy way of constructing a relaxation superoperator without fussing about the mechanistic details. And that's good enough to be able to do some calculations with it, which give insight into magnetic resonance experiments. So let's look at some examples. So let's suppose we go back to the single spin system, single spin half. And we use the trajectory command. In this case, I'm simulating, if you remember how this works, I'm assuming the density operator, the starting density operator is Ix, so transverse magnetization. And I'm going to track what happens to that same operator, Ix, under evolution under the Liouville-von Neumann equation, in which the generator is given by a phenomenological relaxation superoperator with a T1 equals T2 of 1 second in this particular case. And we're going to track it over an event which is just do nothing for 5 seconds. So a delay of 5 seconds, start with Ix and then just let it evolve. And then we simply plot the result. And it's not a big deal, it's just a decay. So the Ix operator evolving under this relaxation superoperator, which has a T2 of 1 second, simply decays as an exponential. Now I suppose we not only have the relaxation, but we have a Hamiltonian as well. So we can do that by, in the background, we have a generator which is now a combination of the relaxation superoperator and a Hamiltonian, so now a coherent part of the Liouvillean. So in this case, I'm using here an IZ operator multiplied by 5 Hertz. So that means a magnetic field in the rotating frame which causes a 5 Hertz precession around the Z-axis. So the simulation in this case simulates the precession of the X magnetization around the Z-axis at the same time as a decay. Let's simulate not only the trajectory of the X magnetization, but also the Y magnetization, which we can do by just adding a second operator in the target list. And then we can plot both of those in the plot routine. And now we have the superposition of two plots, one for the X magnetization, one for the Y magnetization. So we have the trajectory of the X magnetization as it decays and also precesses around the Z-axis. So what we're simulating here is something like this, that the magnetization starts along the X-axis and then now rotates around the X-axis in the XY plane, but at the same time decays under the T2. And we'll see that in a more attractive graphical form in a minute. Okay, so that's what happens to the X magnetization. Now let's have a look at the Z magnetization. So we can do exactly the same thing. So this time we have a trajectory starting with Z magnetization and tracking what happens to Z magnetization in the presence of a relaxation superoperator with a T1 of 1 second. Well, it behaves exactly the same as the X magnetization. Not surprisingly, because the relaxation superoperator looks exactly the same. And T1 in this case is equal to T2. So the relaxation, the phenomenological relaxation superoperator, if you remember what it looks like, that's shown up here, is just -1 over T1 for the Z operator. That was this fourth column here. And -1 over T2 for the X and Y operators. So the Z magnetization just decays. However, when we learn about magnetic resonance theory and the Bloch equations, we know that that's not what's supposed to happen. The Z magnetization does not decay to 0 at long times, but it decays to a position of thermal equilibrium. And we're going to have to cover how to put that into the calculation correctly. So this is not a physically correct result. The Z magnetization of a spin system in a sample at finite temperature does not decay to 0. It decays to a finite value, the thermal equilibrium Z magnetization. So if one tried to calculate using this phenomenological relaxation superoperator, one would get some puzzling results concerned with the behavior of the Z magnetization. This, for example, would be a simulation of an inversion recovery experiment in which I start with the initial IZ density operator and track the value of IZ. This time my pulse sequence consists of a delay of half a second in which nothing is done, just inserted for graphical convenience there. And then a pi pulse, or a 180-degree pulse, which inverts the Z magnetization, and then a delay in which we observe what happens. Again, we're in the presence of this relaxation superoperator. And the result looks a bit strange. The initial Z magnetization decays during that initial delay, is now inverted by the pulse, and now continues to decay to 0. And we know this is not correct. This is not what should happen. If we're interested in simulating accurately spin systems at finite temperature, then we have to learn how to get the correct behavior. And this is a topic which is a pretty tricky one, actually, called thermalization. Now, if we go back to the Liouville von Neumann equation, so it was the time derivative of the density operator is given by the Liouvillean multiplied by the density operator. So this is the Liouville von Neumann equation. And the Liouvillean has a coherent part and an incoherent part in it. Which here I'm just going to call gamma. And we've seen actually that without immediate intervention that this does not actually give the experimentally observed evolution of the spin system. And actually this has been a long-standing puzzle or problem in theory of magnetic resonance. And there's actually two ways of addressing it, both of which are not entirely satisfactory, but they work. There's two ways to go here. One is to fix the Liouville von Neumann equation. And this is done simply by changing the equation. So it now looks something like this. So the equilibrium, the thermal equilibrium density operator has been introduced as an extra term in the Liouville von Neumann equation. And this is done to account for the fact that the lattice, or the molecular environment with which the spins interact, have a finite temperature. And that's actually the most common way of doing it. And if you look in the standard textbooks on NMR theory, that's the sort of equation which will be used. So you could call this the standard way. Now, personally, I don't like this because it spoils the structure of the Liouville von Neumann equation. And it turns out there's another way of doing it, which personally I find preferable, and which is the method used in SpinDynamica. That's to modify the Liouvillean, or in fact to the relaxation superoperator. And there's a technique for doing that which I'm not going to go into the details of. It's described in various papers which I can give you the references for if you're interested. But it's a procedure which can be implemented in the computer and which is implemented in SpinDynamica. So basically one can construct a relaxation superoperator or use the phenomenological relaxation superoperator and then just correct it for the finite temperature of the environment. And then everything remains the same. One can just then use that superoperator throughout the rest of the calculations. So I'm just going to show you how to do that. And I have to say it is a little bit of a messy subject, but I don't really know if there's a neater way of doing it. The fact is, actually, in very many magnetic resonance calculations, one doesn't actually need to do this. But in some effects where one does need to take into account the thermal equilibrium density operator, then to get the correct result, then it does have to be done. So the steps are as follows. One has to correct the relaxation superoperator. That's point 1. Point 2 is that one has to give up that approximate density operator. If you remember, I think last lecture, I said that when we call the density operator IZ, that's incorrect because IZ does not have trace of 1. And a density operator must always have trace 1. So there's no way around it. We have to go to a rigorous density operator which does have trace 1. And then finally, the results of calculations should then be normalized against a physical result, which is the thermal equilibrium magnetization. So let's just see this. So we start with a single spin system. And we have to figure out what do we need to thermalize the relaxation superoperator. We need two things. One is we have to specify the temperature of the environment. Thermalization implies that we correct the Liouville von Neumann equation for the temperature of the environment, which is not infinite, it's finite. We need the laboratory frame Hamiltonian, which defines the thermal equilibrium position of the density operator. So here's an example. First of all, here I calculate the Larmor frequency of protons, that's the 1 here, in a field of 18.8 Tesla. Having converted into Hertz by dividing by 2 pi, we see that the Larmor frequency is 800 megahertz, and it's negative because of the positive sign of gamma. The laboratory frame Hamiltonian is simply the Larmor frequency multiplied by Iz. So this is what causes the splitting of the energy levels in the laboratory frame. And the temperature, let's just assume it's 300 Kelvin. So we thermalize the relaxation superoperator. So here I've just set up the spin system again. That was already done, so that wasn't necessary. Let's define the relaxation superoperator as before for T1 equals T2 of 1 second. Just to go through this again, the relaxation superoperator as a matrix is a 4x4. These three elements referring to the relaxation of the transverse components, Ix, Iy, and Iz. Since in this case they're all 1 second, then I just get -1 for all of those terms. I could use matrix plot to just represent that as in a graphical form instead. And here's our 3 diagonal elements. And now we thermalize. So here I've defined a new symbol, gamma therm, which is created by thermalizing the superoperator gamma using the laboratory frame Hamiltonian and the temperature. And let's see what it looks like. It's still a 4x4 matrix, of course, and it still has the 3 elements along the diagonal of -1, but it has a new element which curiously is on one side of the matrix but not the other side. And it's this strange element here which corrects the Liouville von Neumann equation for the correct temperature of the environment. And it actually connects the unity operator to the Z operator. We can see that again in graphical form here. So now there's a new, very small but finite element in the first column of the matrix. And that term basically does the job for us. Let's see how it works. So we also need to define a rigorous density operator to start the simulation with. Just Iz is not going to do. It's got to be something rigorously defined. And we can do that with thermal equilibrium density operator. Again, using the laboratory frame Hamiltonian and the temperature. And that operator now is given by, has a very small term because of the small degree of spin order in thermal equilibrium proportional to Iz. So that represents the weakly polarized spin system we get in thermal equilibrium at ordinary temperature in ordinary magnetic resonance experiments. Okay, so we have the thermalized density operator, thermal equilibrium density operator, to start the simulation with. And we have the thermalized relaxation superoperator, which gives the correct equation of motion for a spin system evolving at a finite temperature. And it's going to be useful actually to determine what the coefficient of Iz is in thermal equilibrium, so we can then normalize the results of calculations against that. We don't really want to be plotting these very tiny numbers. We'd prefer to be plotting something which starts at 1. So we can calculate that, and that's just using the operator amplitude routine, which basically asks SpinDynamica, what's the coefficient of Iz in the thermal equilibrium density operator? And it's this small number. So now let's look at the calculation, but this time with thermalization of the superoperator. So again, we use the trajectory routine, starting though not with Iz, which is not rigorous, but with the thermal equilibrium density operator. And we can track what happens to the operator Iz. And we have again the same inversion recovery sort of sequence, a delay of half a second, just for graphical purposes, a 180-degree pulse, and then another delay in which we're going to track what happens to the magnetization. In this case, the background generator is just this relaxation superoperator, but now it's been thermalized. And so we get an attractive normalization on the result, then we normalize against the magnetization in thermal equilibrium. And now the trajectory looks more like magnetic resonance, people who know magnetic resonance theory would expect to see. So the Z magnetization starts with 1 because it's in thermal equilibrium, and because the trajectory was normalized against that value. So the starting value is 1, and then it's inverted by the 180-degree pulse, and then relaxes, but not to 0 now, but back to thermal equilibrium. So this is now the expected result, and we've simulated an inversion recovery. And we can now simulate also anything else to do with the motion of magnetization in the presence of relaxation, taking into account the fact that the temperature of the environment is finite. So here's an example. So here I'm going to do a 3D calculation. So I have 3 trajectories for the XYZ magnetizations. Again, I start with thermal equilibrium, and this time track the 3 operators X, Y, Z. And here I've just chosen to do it with under a pulse, a 90-degree pulse along the x-axis, pulse as being 1 millisecond, and then a delay after the pulse in which we'll see what happens to the magnetization. And the generator acting during the Liouville-von Neumann equation is a combination of this thermalized relaxation superoperator and again 5 Hertz precession around the z-axis, with all trajectories normalized against the thermal equilibrium magnetization. I get 3 trajectories, and then I can plot using the parametric plot 3D routine of Mathematica to get a magnetization, typical magnetization trajectory, in which you can see the effect of the first 90-degree pulse, which has tipped the Z magnetization down to the minus y-axis, and then afterwards it's started to precess at the 5 Hertz in this case around the z-axis. And at the same time as precessing, it's also relaxing. So the the X and Y components of the magnetization are decreasing with T2. And also the Z component is recovering back to thermal equilibrium along the Z axis with T1. So with that syntax, one can readily explore what happens in different circumstances. So if we just copy that, choose to insert, for example, after 1 second, we could insert a 180-degree pulse about the y-axis. Maybe give its duration twice as long, and then insert another subsequent delay after that. We can just try to simulate that and see what happens to the magnetization in this case. An interesting result. We can think about what that possibly could mean. Clearly we have the 90-degree pulse to start with, and then it precesses, but then at some point the 180-degree pulse is hitting and flipping it down again. The 180-degree pulse was chosen to be along the y-axis, so it will invert the X component of the magnetization, but also the Z component. So it's being flipped down. By the time that pulse had arrived, the magnetization had partially recovered towards the positive Z-axis, but then the 180-degree pulse bounced it down again, so it went down here, and then it has to continue its precession and to relax back up again. So it's useful to experiment with this, and you can explore many different features of magnetic resonance for spins a half using this type of routine. So I think with that I'll end this lecture.